Hello and welcome to this presentation on real-time video streaming on the pubs of architecture. A case of Apache Kafka. And my name is Toby Ahmed from Hiroshima University. So, getting right into it. So, the, the idea is that pub sub architectures are mainly used for event-driven use cases. When events are fired up and you want to kind of like concurrent and independent operation of components as well as an immutable chain of events, right? So logs, for example, and events, for example, in let's say banking systems or IoT systems and transaction event processing. So use cases like this are like the most suitable for pub sub architectures. Definitely not suitable for video streaming, and it has come to it would come as a shock as in why we're studying video streaming on PubSub at all. And so the first thing first is to establish the why of why we're using PubSub or why we're studying video streaming on PubSub platforms, given the diverse spectrum of the types of PubSub platforms and the plethora of various configuration parameters that necessitate a thorough consideration to achieve such video streaming. It's like, why don't you just use already available platforms like WebRTC or so on? So now the answer is that there is particular use cases, um, particular niche use cases where you're trying to support event-driven use. You're trying to support an event-driven use case together with video. So one of those is PARM, physical activity recognition and measure, which is let's say an example would be recording brainwaves um, using an EEG device, for example. And so in that case, we want to transmit EEG data, event data, right? It's event processing, and whenever a user does something, and whenever the test, the experiment, you know, has some sort of stimuli, and we want to record that, and we want to record the peaks and troughs of the user's EEG trend and data and so on and so forth. And in this regard, it would be important to also, along with it, have video data of the time that the time that or at the time that the stimuli happened. And one of those basically one of solutions to that would be that using the same event driven kind of architecture, like let's say a PubSub platform, then on it we send video as well together, coupled and or separately in different topic, you can say. And so there is different particular kind of use cases um, where for example, real-time video analytics and IoT devices with cameras, surveillance systems, where we want to handle data and video frames together. Um, yeah, and we want to handle video frames basically, particularly in an event-driven setting, so to say. And so, I mean, it makes its features. It makes Kafka in this case, which is the PubSub platform of choice for this study. Kafka is suitable for specific use cases where reliable, scalable, and real-time data processing is required. And so, I mean, one of the benefits of that is that you can get high throughput data ingestion and real-time processing if you, let's say, further integrate it with, for example, Apache Spark um, and so on and so forth, the similar technologies. And so, yeah, and we can also have a plethora of consumers on the PubSub platform, and it's easy to basically incorporate them. But in this case, it kind of like um, it forces us to think about now the parameters that are required or that should be considered in terms of um, supporting video streaming, proper video streaming, and on the PubSub platform. And uh, so that's where the study would come along. We want to delineate essential parameters and operational requirements and specifications for achieving a low latency real time keyword real time video streaming via the PubSub pattern. Yeah. So um, yeah, so by investigating operational parameters and video quality assessment methods, we can basically redefine some of the use cases where PubSub platforms may be leveraged for optimized video streaming. Um, so experimental setup. So what were the, for example, software libraries used? So in this case, we used SINETStream. So SINET is a nationwide academic network in Japan, and there's a Python library, Java library, and so on, which basically kind of like a software package on top of SINET, of course. Not only SINET, of course, but other IoT communication platforms. It's a closed network for universities nationwide in Japan, and so it was basically the underlying network of the study. And the PubSub platform used was Apache Kafka, and it's widely recognized as a distributed streaming platform, efficient implementation of the PubSub pattern, and also VidGear. And VidGear is basically it's like a library built on top of OpenCV. There's a lot of other media libraries inbuilt in it, and it provides um, a lot of media libraries for media processing, basically, and including real-time video stream capturing, processing, streaming, saving, all with minimal latency and optimal performance. Um, yeah, and then yeah, all classes and tests were conducted on an i7 4-core Ubuntu 22 system and using a 30 frames per second webcam. And so the idea is that the webcam um, frames were captured from the webcam. Yeah, so so other components include multithreading, the sender, receiver, classes, and one for frame capture. So as I was saying, that the whole picture is that frames were captured from the webcam, and and basically the first thread gets or captures the frames, and the main thread basically is weaving the two threads together and sending the the frames to the other thread, the sender thread, which sends to mobile SINET using Kafka, and the receiver does pretty much the same, vice versa. One thread fetching from SINET, retrieving the frames, and decoding, and uh, the thread is showing the video. Okay. Um, Although not written explicitly um, at the beginning, but another one important library that was used was libjpeg turbo, which is basically a JPEG image codec, image compression through the JPEG. Um, the importance of this is that the frame, so the frame basically when it's obtained here, the main thread basically kind of compresses that and then sends it to the second thread. So compressing the frame enables that the frame size is significantly reduced. And the benefit of this JPEG library is that it can be interchanged with any other JPEG library out there. It could be most JPEG or Quetzal by Google, or CV2 JPEG also. So any other library that basically does JPEG compression is can be plugged in and plugged out here. And the progressive interpol coding executes image encoding process in multiple passes and leading to an optimized compression ratio. And one thing that gives us in here is it offers the ability to choose the amount, the percentage of the image quality to retain at the end. How much image quality should be after compression? Should you retain 100% or 80%? So, for example, in that case, 100% would mean the highest quality an image can retain after compression, and that means the highest message size as well. So the full picture is that we capture the frames from big gear and encode the frames using libjpeg frame by frame. For each frame, we compress the frame using the JPEG compression, and then we send the frames to Kafka using the producer, and receive the frame from Kafka. As consumer will do from the broker, decode the frames from libjpeg's encoding, and then we show the frames using vidget. So the main discussions or main results is that the first thing is first is that now the definition of optimization of such a system would be, or the physical parameter definition would depend on the type of system. In that case, for example, uh, uh, yeah, so there's three criteria: latency, throughput, and video quality, which, for example, in teleconferencing, well, video quality, aside from just having good throughput or latency, video quality is, well, an important part of the use case. We need to be able to see who we're talking to and hear them well, something like that. And in that case, then, well, one has to make the trade-offs for latency and throughput for video quality. Um, and I mean, in a different case, whereby, for example, it's a video surveillance platform and video surveillance system, say security surveillance, and it's just Raspberry Pi cameras at multiple points, given, let's say, multiple points in a building, transmitting to a broker, then video fidelity is necessary, but also latency has to be good, for example. So different use cases will offer different kind of a set of requirements. Do we need 4K video in a surveillance camera footage? Of course not. Well, that would be kind of like a standard or a requirement in the teleconferencing use case, for example. So, I mean, because I mean, in Kafka, it is possible to have a low latency transmission, but a very poor visual fidelity due to inadequate receiver buffer and insufficient other parameters that need to really be configured. And the second thing is that, well, broker versus partition relationship has to be considered. And so there's a kind of a ratio that has to be considered. How many brokers and how many partitions you're gonna have per broker, for example. And um, and so if you have a high number of partitions, then you're going to have a lot of turnovers and a high latency due to a lot of rebalancing every time a consumer joins or leaves the consumer group. And so for scalability, then it's not just about increasing the number of partitions or increasing the number of brokers, because that's going to increase the, let's say, replication factor. And it's going to increase the broker CPU overload, because it has to check every partition and there's a lot of replications of the data, and so however, yeah, there has to be a ratio between number of brokers versus partitions, as well as the message size or the number of consumers in the system, so that there's a perfect balance as the system grows. To strike a balance between latency and throughput, right? So you will have, for example, the average repeated frames here for one partition, meaning one partition is not good for throughput, a lot of repeated frames because there's no concurrency in the system, and the pattern begins to, I mean, it really doesn't go down anymore than it could, because there is a, so when partitions start increasing again, then the similar, basically, performance does not increase as one would expect from this video. So in the terms of average repeated frames, we want frames. In the case of video streaming, we don't want a lot of repeated frames. Well, this would be the case in another, wouldn't be the case in another use case whereby repetition of frames is not a problem. In a video streaming use case, lags because there's basically repeated frames. And so this has to be considered, and one partition is definitely not ideal for any use case on a PubSub platform. And in the middle, depending on the number of brokers, so four would be four, eight, four would be the best. And in terms of average repeated frame, but when you look at latency, then you'd say, well, two partitions is the best, because, well, um, the brokers have just the right amount of concurrency and parallel processing without the overhead of managing all of the partitions, which, I mean, the overhead increases when the partitions also increase. And so it is, to keep the latency minimum, you'd have to consider a good broker range. And in this graph, the blue shaded region is basically the jitter, and the actual line itself is the latency. And so when you look at it, it's okay. That, so the jitter and the average jitter, uh, as the partitions increase, so has to be considered. And so it's not just about, well, have as many partitions as you want, but reasonable partitions for each use case, and particularly for the message size. And continuing that, so basically saying the same thing, that, well, when you look at now the combination of broker and partition, a picture emerges whereby, for example, if you have 2 2 here, low, then you have 4 2 here, and 8 2 here. So two partitions for each broker performed well in our case, for example. And so, depending on the message size and the number of consumers in the system, the number of partitions has to be selected carefully to complement the number of brokers, also as well. Um, Compression. So compression is one of the most important aspects of this, in that the efficiency of the video streaming platform, it hinges upon it. And all video streaming platforms out there have to have some sort of codec for compression. And so the JPEG compression that we use, the library that we use in this, offered significant compression from 2.7 megabytes to about 300 kilobytes in 720p resolution. Um, and so it is very important to watch the relationship between the compression and the message size, or frame size in this case. And basically, future research would be basically tuning this to kind of like mitigate network conditions. When network is good, then we can have a high quality, and vice versa. Okay. So looking at that, so basically the relationship between compression, the compression amount or image quality, compression quality, basically retained, the misnomer here is retained compression quality would be, okay, So after compression, how much percentage of the image do you still want to remain in your image? So 0% would be basically undiscernible and terrible quality, while 100% would be basically mimicking the original image as much as possible. And so in this case, it would be it's very key that the compression lies between 20 to 60%, and it should vary based on network conditions to kind of um, have an adaptive kind of compression and message size based on network conditions. And finally, we want to talk about the video fidelity considerations, whereby it's not just about latency or throughput, but also about whether the video itself was pleasing, because Kafka can achieve a low latency, but if the buffer, for example, factors like the buffer and consumer sleep time are parameters that basically, if not considered, you can have a situation whereby the consumer receives the frames as early as possible with low transmission latency, but doesn't have the time to piece them together or decode time. It is all over the place, and basically the buffer is too small for the consumer processing, and so the video may still look laggy and unpleasant for viewership. And so video stream quality is a factor that has to be considered based on the use case in terms of the earlier example that I already gave. Okay, if it's a use case that requires, like for example, a video on a drone, then that will require more video fidelity considerations. No one wants to see a kind of laggy video on that, and so it depends and has to be considered as well. Talking about the conclusion, so our study goes beyond traditional data transmission research to investigate the use of PubSub platforms like Kafka for real-time video streaming. Why? It's because Kafka has a lot of benefits, and we want to explore whether these benefits um, can be applied to video streaming as well, to especially in specific use cases where the data and video in event-driven scenarios has to be coagulated together or has to be complemented in this case. And future research includes scalability of such a platform and dynamic optimization, moving away from static definitions of parameters. So that, for example, partitions that dynamically change based on the number of consumers or the message size or the frame size, whatever camera is being, maybe 60 frames per second now. So the system has to adapt to that. Reaching here, thank you very much for listening. Until next time.